In the last video, we saw how parity could be used to detect any single bit error that occurs when transmitting from one system to another. And we can inject an error here to sort of demonstrate that. But the limitation of parity is if there's more than one error that occurs in your message, then it may not detect it. And actually, in this case, that seems to be what has happened here. So for example, we have a comma in our hello comma world. Over here, no comma, so there was definitely an error. And of course, I injected an error, you saw that. But our received parity is even, which indicates that we did not detect a parity error, even though there was an error. And that's just the limitation of parity, is if there's one bit error, you're guaranteed to catch it. But if there's more than one, depending on how many errors there are, you basically have a 50-50 chance of catching them. And then at the end of the last video, I showed you some potential ways to work around this by potentially adding more parity bits. So if we have our message here, hello world, we can convert that to binary. We've got the binary representation of what we're sending. And, just for basic parity, we have a single parity bit. And in this case, if we count up all the ones in this message, there are 49 ones. And in order to send this with even parity, we want to send either 48 or 50. We want to send an even number of ones. So we have 49 ones. We need to add another one so that we send an even number of ones. But if we change any two bits in here, for example, we just change any two ones to zeros, instead of having 50 ones, we'll have 48 ones. That's still an even number, and so we won't detect a parity error. So one way to work around that is to add more parity bits. So instead of having a single parity bit for the entire message, we can have a separate parity bit for each byte. And of course, the trade-off is if we're sending a parity bit for each byte, then we're sending more data overall. Because we're essentially adding 12% overhead to our entire transmission. And maybe that's worth it because you want to catch errors. But even here, you still may not catch every error, because if you have multiple errors in a single byte, then you may not catch that with the parity bit. And so you could keep going. You could say, well, we'll send a parity bit for every 4 bits, or a parity bit for every 2 bits, or even a parity bit for every bit, which essentially just means you're sending the entire message twice. But all of that just adds more overhead. And so it seems like there's this trade-off, right? So in this video, I want to talk about some ways to sort of do better than this, to get a better error detection, but lower overhead. That's sort of our goal here. And one thing to keep in mind is just the types of errors that we might expect. So it's actually not true that it's equally likely for every bit to just randomly flip. Errors tend to happen in certain patterns. So for example, the error that we had here, where we were supposed to be receiving hello comma world, but we received hello and then 2 spaces. That error happened because of 2 bit flips. So if we look at the difference between a comma and a space, it's just these 2 bits, right? It's 0010 in both cases, and then it's either 1100 or 0000. And so what happened while we were transmitting this is I just hit this button to drop those 2 bits, and that's what injected the error. And because it was 2 bits that flipped, we didn't catch it with the parity. But we wouldn't catch it here either, right? Because if those 2 bits flipped, then this parity bit's still going to be a 1, right? Because we'd go from 3 ones in here to just 1 1 in here, and that's still an odd number, so we'd still have a 1 out here as our parity bit. So we still wouldn't catch it with even this scheme. And in fact, this type of error where you have multiple bit errors in a row is called a burst error, and it's quite common. Because you might imagine some sort of thing interfering with your signal. Maybe it's not a button like this, but some sort of interference that happens. It's going to happen, over maybe some short period of time and corrupt a couple different bits in a row. So one thing we could do with parity that's actually much better at catching burst errors is, instead of using a parity bit to protect a sequence of bits in a row, have the parity bit protect an interleaved sequence of bits. So one way to do that is something like this, where we have the same data here, but instead of computing a parity bit for each byte, you essentially compute a parity bit for each column here, which is sort of each bit position within the byte. So for example, if we look at the first bit of every byte, well, in this case, they're all zeros, so the parity bit is a 0. And we just do that for every bit position. At the end here, we're going to have essentially another byte of 8 parity bits. And so we send our message, and then we send these 8 parity bits. And this is much less susceptible to burst errors. So for example, if we change both of these bits here, like we did in our message where we lost our comma, we would detect that because both of these parity bits down here would be invalid. And now this still has limitations, of course, right? So just like here, if we change 2 bits in a row, we wouldn't necessarily detect that. Here, if you change 2 bits in a column, you wouldn't detect that. And so there's this trade-off between parity bits per row versus parity bits per column, and which one you might choose depends on the types of errors you might expect. And in most communication systems, burst errors are actually pretty common. And so something like a parity bit per column here might be a better choice. But know that you may not catch multiple bit flips in a column. So that's the trade-off that you're making. But maybe we don't need to make that trade-off. A few of you suggested in the comments on the last video using a checksum. And the term checksum can technically refer to any additional little bit of information that you attach to your message to validate that it's correct. But it can also literally mean a sum. So if we take the characters in our message and get their ASCII numerical equivalent, we can just add those up. And in the case of Hello World, we get 1161. And so what if we just send our message and we send this number 1161? Well, then you'd think, well, if anything in here changes, well, then the sum's probably going to change. So is that better or as good or worse than these parity things we've been looking at? Well, to figure that out, it actually helps to look at this addition in binary, because we can do the addition in decimal like we did here. We could do the same addition in binary. We should get the same answer. And in fact, this answer we get here is 1161 in binary. But if we look at the way this addition works, there are actually a lot of similarities to parity going on here. And so we can actually sort of compare what's going on here to what's going on with the parity scenario where we were taking a parity bit for every column. Well, it turns out that actually for this first column here on the right, it's the same. Because if we just count up how many ones there are, which I guess is the same as adding them, we get 1, 2, 3, 4, 5. And so the sum there would be 5. Of course, there is no 5 in binary, so the way you represent 5 is 1, 0, 1. So you would put a 1 down here, and then we carry a 1, 0 over into these next columns. So the 5 here is 1, 0, 1. But if you actually look at this 1 that we're putting down here at the bottom, this is identical to a parity bit for this column. Because if you add up this column, or you count the ones, however you want to think about it, if the answer is even, then it's a multiple of 2. And in binary, a multiple of 2 is going to have a 0 in the last place. Just like in decimal, if you think about a number that has a 0 in the last place, it's going to be a multiple of 10. On binary, base 2, if you have a 0 here, it's a multiple of 2. And if it's not a 0, which, in binary, the only other option is that it's a 1, then it's not a multiple of 2, which means that it's odd. So this bit here essentially is a parity bit for this column. And then the next column works the same way, right? We add these up, and there's 1, 2, 3, 4. So there's 4 ones in that column, or you can think of the sum being a 4. That's even, so you put a 0 there if we're doing parity, but if we're adding, then 4 is 1, 0, 0. So you put the 0 there and carry the 1, 0. So 1, 0, 0, and you carry. But what's going on that's different than parity here shows up when we get to the third column here. When we add this up, in the third column, we get 1, 2, 3, 4, 5, 6, 7, 8, 9 ones. But it's actually 10 ones because we have this 1 that we carried from the first column. And so because it's 10, that's, what was it, 1, 0, 1, 0? So we put a 0 down here and carry the 1, 0. So it's 1, 0, 1, 0. And so what's interesting now is that this number here is not the parity bit for this third column from the right as it was originally. It's the parity bit of the third column from the right plus what was carried in from these other additions over here on the right. And so in some sense, you can think of what we're doing here with this addition as being very similar to computing a parity bit for each column, but we're kind of holding on to some extra information when we do that. And then that extra information is percolating over into the columns to the left. And so in some sense, we're getting kind of the best of both worlds here, which is that if we have a burst error and several bits change within a single row here, then we'll catch that in our checksum down here. But also, if several bits change in a column, we may catch that as well. So for example, if both of these 1s were to change to 0, the parity wouldn't change, so it'd still be a 1 down here. But it would be a 1 because the sum of this column, instead of being 5, would be 3. And so while this wouldn't change, what we carry does. So instead of carrying a 1, 0, 1 for a 5, it would just be 1, 1 for 3. So that would change the parity of these next two columns, or the sum, if you want to think of it that way, of these next two columns. And so we're able to catch that type of error here. Now in practice, you may not actually send the entire checksum like this, because if we're sending 8-bit words, oftentimes what you'll do is you'll just chop off this first part here and just send 8 bits of the checksum. And that's a pretty common thing to do. And you can think of that as essentially being equivalent to sending the remainder of a division problem here. So if you add it up, you get 1161. If we divide by 256, we get 4, which is the part on the left there. And then the remainder, 137, is the part on the right. And we just send that as essentially as our checksum. That's a pretty common way to do this, because if you're already sending 8-bit words, it may not be so easy to just send an extra 11 bits. But of course, the drawback of lopping off these leftmost bits is, what we just talked about, this sort of information that percolates over to the left here, you'd end up losing some of that. And so one thing that's done fairly commonly is to do an end-around carry, where you take this extra bit that you've had there and you essentially add it back to your original checksum. So you just sort of lop that off, move it around here, and then add it. And then you end up with this number here. And essentially what that does is that you're doing this sort of end-around carry. So when you're adding these leftmost columns here, instead of carrying off to the left, you're essentially sort of carrying back around to the right here and taking this extra information and holding on to it over here on the right side of your addition problem here. And so this ends up kind of retaining some of that information. Incidentally, this technique of doing this end around carry like this when you're doing addition is referred to as one's complement addition. And it has a few other interesting properties. I won't go into all of that right now, but if you're interested, I would encourage you to go look up one's complement addition. So now if we do this end around carry, it turns out that actually what's going on here is instead of dividing by 256, what we're essentially doing is dividing by 255. And it might be interesting for you to sort of think through why that's the case. But essentially, we take our sum here, 1161. If we divide that by 255, this remainder, 141, it's actually 4 more than 137. That's what we end up with here is our final checksum, if you will. But one technique that's kind of interesting is rather than sending our message followed by a checksum of 141, we can send our message followed by sort of the inverse of that. So if we just flip all of the bits, we get this other number. I think this is 114. And it ends up being the same as 255 minus 141. If we send this as our checksum, so for example, if we send our message followed by this number, this 114, when we do our addition, we do the addition the same way, and then we end up with this little bit over here, so we can add that in, and then we add that together, we get all ones, and then if, again, we flip all the bits again, we get to zeros, and that's essentially a very quick way to check that we got the right checksum. And that's an interesting side effect of this ones complement addition, where essentially what we're doing is we're adding and getting the remainder when we divide by 255. And because we can just easily flip the bits to get 255 minus this number, when we add that in, when we add this up, including this checksum, assuming nothing has changed, we would expect to get a multiple of 255, and that's sort of what we end up with. So this is a very clever way to do a checksum. And in fact, this is the exact technique that is used in what's called the Internet Checksum, which is a checksum that is performed on every IP packet on the internet. The only difference is that for the Internet Checksum, the data is chunked up into 16-bit words instead of 8-bit words. But otherwise, it's the same thing. You add it up, you carry this bit that's carried, you wrap that around, add that together, flip it, and then that becomes the checksum. And then you can validate it just by doing that same addition, wrapping around, and you'll end up when you flip it with all zeros, assuming that it's correct. And that's how the Internet Checksum works. Obviously very widely used, but the checksum still has limitations. And to think about what some of those limitations are, you can think about, since we're doing addition here, one of the things about addition is that the order that you add numbers in doesn't matter. And so the order that these bytes show up also wouldn't affect the final checksum validation. So if we received this message and each of these letters was just like flipped around in a completely different order, we'd get the same checksum, and we have no way of detecting that had been reordered like that. So that's one limitation of this type of checksum. Now, another limitation could be, data being inserted or removed. Now, obviously, if we inserted just a random byte in here, we'd probably detect that with our checksum, or if we removed any of these bytes, we would certainly detect that with our checksum. But if you just inserted a bunch of bytes that were all zeros, you wouldn't have any way of detecting that. So just in the middle of our message, if we, instead of having this 13 character message, it turned into a 20 character message, and there were just like a bunch of zeros inserted. We would receive the wrong thing, but the checksum would be the same because when you add in a zero, it doesn't change the result. Same thing if our message had some zeros in it. Now, in this case, none of our bytes are just all zeros, but if we had some zeros, some bytes that were just all zeros, if some of those bytes got removed from our message in transit, again, it wouldn't affect the checksum. We wouldn't be able to detect that. And you may be thinking, extra 0 bytes getting inserted into our message or bytes arriving out of order. That's unlikely in our application here. And that's certainly true. I mean, we're definitely not going to get things arriving out of order because, our transmission here is just a wire, right? Every bit that goes in the wire on this end is going to come out of the wire on this end in the same order. Like there's just nothing in here that's going to cause them to be out of order. But in more complex networks, data arriving out of order is actually quite possible because there might be multiple paths to get from point A to point B, and some data might go across path 1 and other data might go across the other path. And if those paths don't take quite the same amount of time, some of the data might show up before the other data, even though it was sent after it, and you get data out of order. So you'd want to be able to detect that. And so something like the checksum that we just saw might not be able to catch that. Now, there are ways to use checksums that are able to detect out of order data. And just as an example, one common sort of low-tech way is these ISBN numbers that are on the backs of every book. And there's a couple different formats. There's a 13-digit format and a 10-digit format. I'll look at the 10-digit one. And basically, if you look at this 10-digit number, there's 9 digits, and then this last digit, in this case the 6, that's actually a checksum of the other digits. And it's a checksum that also is able to detect if any of the digits get swapped. And in this case, that's important because you might imagine somebody is typing this number into a computer and they just mix up a couple of digits. Instead of 465, they put 456 or something like that. You want to be able to catch that and have the computer say, oh, that's not a valid number. So the way this works is you've got the ISBN number here, at least the first 9 digits of it. And the way that we calculate that last digit, that 6, is that instead of just doing a simple sum of these digits like we would for a normal checksum, first what we do is multiply them by a number that indicates the place that they're in. So we multiply the first digit by 10, the next digit by 9, 8, 7, so forth, and we get this sequence of numbers here, and this is actually what we add. And so instead of adding 4 plus 6 plus 5 and so forth, we end up adding 36 plus 48 plus 35, and that kind of encodes the place that the number is. And then we end up with our sum. In this case, it's 192. Then to get that final digit, what we do is we divide by 11. So we divide 192 by 11, we get 17. We actually don't care about that part. What we care about is the remainder, which is 5. And it's interesting that we're dividing by 11. That's sort of an interesting choice. And the reason for that is that each of the numbers that we're adding here to get to our sum are the product of two numbers, neither of which are factors of 11. And so what that means is that if either of these numbers change, either the digit or the place, essentially, for that digit, then the sum will change, and the sum will change by some value that's not a multiple of 11. And because of that, we'll know that the remainder that we end up getting will be different if any of these digits changes or if the place of any of these digits changes, which is pretty powerful. That's what we want. And then the other thing you'll notice is that we don't actually put the 5 in here as our check digit. We take 11 minus that 5 and put a 6 as our check digit. So if our check digit ends up being 6, which is what we see on the book here. And the reason for that is this other pattern that you might have started to notice with these error detection codes, which is if we take the entire number with the checksum and compute a checksum of that, what we'll end up with ends up being 0. So for example, here, take 6 times 1, we're going to get 6. Instead of 192, this will be 198. And then if we divide 11 into 198, we get 18, and that goes in evenly. There's a remainder of 0. And that's an important pattern to notice, and you've probably seen that popping up multiple times here. So instead of putting our 5 here, we put a 6, such that when we recompute the checksum including the 6, we end up with essentially a remainder of 0. Same thing happened when we were doing these checksums they're sort of like the Internet Checksum, which is we get our answer here when we do our ones complement addition, but then we invert it such that when we do the same operation with our sequence of numbers, including that inverted checksum, the answer we get once we invert it also ends up being 0. So we sort of apply the same process to the original data plus the checksum, we get a 0, and that's how we validate it. And in fact, this is the same principle we saw with our parity bit here, which is we send our message, and then we send a parity bit, and eventually the parity bit that we're going to send here is going to be a 1, and we send that parity bit of 1 such that when we add that parity bit to our message, we end up with a parity of 0 for the whole thing. So it's that same concept of crafting your check bit or check digit or checksum, whatever it is, crafting that in such a way so that when you recompute it on the receiver, including that checksum, if you received it correctly, you end up with a 0. So that's a pattern we'll see over and over again. Incidentally, because we're dividing by 11, our remainder, and hence our checksum, could be any number from 0 to 10, not just 0 to 9. And so in some cases, you'll see a book that instead of having a number from 0 to 9, it has an X there in that last digit, and that just means that the checksum was a 10. Now, we talked about out-of-order errors and burst errors as potential problems, but of course you can also just have random bit errors that just occur randomly. And in order to think about how good a particular error detection scheme is at detecting these random bit errors, it's a useful concept to think about, which is called Hamming distance. And the Hamming distance is essentially the number of bits that are changed between two messages. So for example, this message hi and this message ho have a Hamming distance of 2 because the only difference between these two messages, including the parity bit, is just these 2 bits have been flipped. And so we could say the Hamming distance between these two messages is 2. But when we think about error detection, what we want to think about is the Hamming distance between what's called valid code words. And a valid code word, well, it depends on the error detection scheme you're using. So if we're using parity like this, then, we have to decide what type of parity. So in this case, we're saying we're going to use even parity. And a valid code word in even parity is any sequence of bits that has an even number of ones. A sequence of bits including the parity bit has an even number of ones. So both of these here have an even number of ones, and so both of these are a valid code word. If you had a sequence of bits where only one bit had flipped, but the parity bit was still 0, for example, then it would have an odd number of ones overall, and so that would not be a valid code word. And the way all this terminology is useful is it gives us a way to quantify how good parity, in this case, is at detecting random bit errors. And so because the Hamming distance between valid code words is 2 bits, that means that you have to change at least 2 bits in your message in order to sort of, fool the parity detection scheme. Well, how about checksums? Well, checksum is actually the same thing. So in this case, I have a message hi, and then I have a message over here, ha, with a parenthesis that maybe got corrupted. And it got corrupted just by changing these 2 bits. I changed a 1 to a 0 and a 0 to a 1, and so the sum ends up being the same. And then the checksum you can see is the same in both messages. And so when we add those up, I get all ones, which is how we validate that this is a valid code word. And so again, with a checksum, you have this concept of a valid code word. And a valid code word is one where, well, when you add everything up, including the checksum, you get all ones. Or you can think about it, you add it up and then flip all the bits, you get all zeros. However you want to think about that. So here are 2 messages. Both are valid code words under the checksum scheme that we talked about. And the difference between these 2 valid code words is just 2 bits. And so the Hamming distance, essentially, between valid code words for checksum is 2 bits. So what does that mean? That means that the minimum number of bits that have to be flipped before you're able to detect an error with a checksum is 2 bits. And so in some sense, checksum is no better than parity. And of course, we've seen that checksum is better than parity in a lot of ways. But at least in this dimension, or in this measurement of Hamming distance, both of them are susceptible to just 2 bits being flipped. They can both be fooled. Well, there are error detection schemes that have a higher Hamming distance. So just an example, if we go back to the parity examples that we were looking at earlier in the video here. Here we have hello world. We have a single parity bit. And as you've seen many times, of course, if you change any one bit in here, then this entire thing will become an invalid code word. But if we have 2-bit errors, then we wouldn't detect that at all. So like I just said, parity has a Hamming distance of 2. But how about this scheme here, where we have a parity bit for each byte? Well, it's the same thing. I mean, we could just change 2 bits in a single row here, and we'd fool this, and you'd have what appears to be a valid message, even though 2 bits changed. So again, this scheme has a Hamming distance of 2. How about here? Well, same thing, obviously. You just change 2 bits in a column, and you'd fool it as well. So Hamming distance for parity, it seems in all of these cases, is going to be 2. But check out what happens when we combine all of these. And we send a parity bit for every byte, but then we also send a parity bit for each column, and then we also send the parity bit here for the entire message, which turns out is also the parity bit for this last column of parity bits, and it's also the parity bit for this last row of parity bits, conveniently enough. Well, if we send all of these parity bits, then it turns out we're able to detect more random bit errors. So for example, obviously, if we change any particular bit in here, we would detect that, because if we change this bit here, for example, then the parity for this row would be wrong, the parity for this column would be wrong, and the overall parity would be wrong. So 1-bit error, easy to detect, just like any other parity scenario. Well, now what happens if we change 2 bits? Well, if we change 2 bits in the same row, then the parity bit for the row is not going to detect it, but the parity bits for the 2 columns will detect it. Same thing, if we change 2 bits in 2 different rows, but in the same column, the column parity bit won't detect it, but the 2 row parity bits will. And in fact, you can change any 2 bits anywhere in here, and try them all if you want, but you can change any 2 bits in here, and you'd still be able to detect that. Well, how about 3 bits? Well, if we change 3 bits, there's a couple different options as to how they're arranged, but you can imagine, well, either all 3 bits are in the same row, in which case the parity for that row would be off, well, and parity for the columns for that matter. But you could have 2 bits in a row that change, and then 1 bit in another row. And this row here, the parity would check out, that would be fine. And then of course this column here, the parity would check out as well, and that would be fine. But this column it wouldn't, right? Because you only have 1 bit that changed in this column. And so you'd still detect that. And in fact, you can try any arrangement of 3-bit errors, and you would be able to detect it. How about 4-bit errors? Well, 4-bit errors, we could change 2 bits in this row, and we would not be able to detect that. The parity for this row would still be correct. And then we could change 2 bits in this row, and same thing, the parity for that row would be correct. And because we can arrange the 4 bits so that there's 2 in these 2 columns here, we won't be able to detect that either. And so finally, by changing 4 bits, we're able to transform this message in a way where we aren't able to detect that there's any error with it. And so it turns out with this scheme, the number of bits that you have to change to go from any one sort of valid encoding, or any what we call a valid code word, to another valid code word is 4 bits. That's the minimum number of bits that have to change. And they have to, of course, be the right 4 bits, but the minimum is 4 bits. And so we would say that this scheme has a Hamming distance of 4, which of course is better than simple parity, better even than a checksum. But of course, there's drawbacks, right? I mean, the obvious drawback with this scheme is the amount of overhead that it takes, right? Because we're adding, an extra bit for every byte. So that's something like 12.5% overhead there, plus an extra byte essentially for the overall message. So we're adding quite a bit of overhead with this scheme. And of course, a longer message means more of these parity bits over here. So there's a trade-off. Again, we're sending more data to get sort of a better, quote unquote, better scheme. And of course, overhead and effectiveness at catching different types of errors isn't the only thing that we care about. We might also care about how easy an algorithm is to implement in hardware. So for example, parity turned out to be very simple to implement with just a couple chips like this, and we're actually computing the parity bit in hardware and sending that along. Checksum, you can imagine, be much more complex to actually try to implement in hardware by ourselves. Yeah, maybe fairly trivial to do in software now that we have these nice little microprocessors where we can do all sorts of fancy stuff. But if we really want to be very efficient, we may just want to compute a checksum in hardware. And so that's another consideration, is how easy it is to implement some of these different algorithms we've been talking about purely in hardware. And so that's why I'm going to talk about one more algorithm in the next video that turns out to be a really powerful algorithm. And that's the CRC, the cyclical redundancy check. And it turns out you're able to devise CRC checks that are able to detect random bit errors. In fact, have a very high Hamming distance. They're also able to detect out-of-order data and very good at detecting burst errors. So almost ideal for what we're talking about here. But that's what I'll be talking about in a lot of detail in the next video, where I'll walk through precisely how CRC works and how we can prove that the different types of errors that it's able to detect. And then we'll get into how all of the math that is behind CRC can be implemented in just a few chips. In fact, not much more than we have here. We'll be able to do an incredibly robust error detection completely in hardware.